Hello, everybody. Welcome to this week's string seminar. We are very happy to have Keshav Dasgupta from McGill, and he's going to tell us about what is string theory as a de Sitter excited state. So over to you, Keshav.
Thank you. Thank you very much for inviting me to give a talk. And I was just looking through the campus photos and I thought, it's amazing. It looks so beautiful. Anyway, the front page is exactly, you may recognize it's from the campus. So the title of my talk is, what if string theory has a de Sitter excited state? So I hope you can see what's, if you cannot see anything, let me know.
It's visible.
It's visible. Okay. The search for de Sitter has become quite intensive in the last few years, with debates ranging from absolutely yes to absolutely no with equal passion. And the neutral ones are the ones working with lambda less than 0 or lambda equal to 0 spaces. I mean, no disrespect for that, of course. It turns out that our answer will be yes, and we'll give a proof to justify our statement. Our result will be based on the following paper. So this is the most recent one I wrote, and then there are a few other papers on the line. And my recent paper with Joydeep was to give an answer to this paper, the first paper, which is here, What if String Theory Has No de Sitter Vacua, by Danielson and Van Riet. And then there are a few other papers, and you may note that I have also cited the paper of Gyadiwali, who also found somewhat similar result a few years ago. And some other related papers are as follows. Okay. So here's the summary of the results. I will discuss the problems of realizing de Sitter as a vacuum solution, and then how to realize it as a excited state, which we'll call it the Glauber-Sudarshan state instead of a vacuum. Why is this a hard problem? And even though it's a hard problem, maybe it's still a doable problem. So before I start, I should say that please interrupt me anytime you want. If anything is unclear, please ask as many times as you want. And also, if you do not disagree, please let me know too. So let me start. De Sitter spacetime as an excited state. So it turns out that the problem starts very early on. To see why I would like to view de Sitter as an excited state, let's take one step back and ask some basics question. With this mind, let us take the following four-dimensional actions. I've taken a four-dimensional action given by whatever term you see over here. There's the curvature, there's the Newton constant, and then there is this cosmological constant lambda, there's the Young-Mills coupling, gauge field, and so on and so forth. Now, if you consider this action, then actually there's nothing to show. We can as well as end the talk right here. The theory admits in four dimension a positive cosmological constant solution, which we can identify with de Sitter spacetime. The issue here is that this little term proportional to lambda, that particular term, actually string theory or M theory actually does not come with a term like that. That is the big problem. So the question shifts to the following, that can we show this little term, which we showed over here, square root of g lambda, can it come from a dimensional reduction of an action of this particular form? Okay, so maybe one can think that, okay, this is the curvature term. I can dimensionally reduce to go down to 4 dimension, and there are so many terms over here. All of these terms could conspire to give us that minus lambda over 2 piece over here. So it looks highly possible that we can get an action of that particular form in 4 dimension with such a action we have in string theory or in M theory. So just to let you know, if you haven't seen this before, so this is a 4-form flux. If you haven't seen this particular notation, this is the 4-form flux over here. This is the 3-form field, and then this is this polynomial in the curvature and so on, and MP stand for the M Planck. And note that this action has no scale other than M Planck. and the size of the internal manifold. So in 4 dimension, the Newton constant Gn and G square Yang-Mills should come from only these two particular scales. So that's one good thing about string theory, that there are not too many scales. So everything else comes from M Planck or size of the internal manifold. Now, I asked you the question whether it's possible to get this square root of G lambda in string theory. The answer is actually yes. It's not no. The answer is yes. If lambda is negative or 0, you can easily get that particular piece. However, if lambda is positive, then it appears that it's not possible to get a term like that. You may say that it's a very bold claim, and maybe quantum term. So we see there's a lot of term in string theory, quantum term, perturbative, non-perturbative, and all kind of terms. They should all conspire to give us that positive lambda solution. So it's too early to say that such a term cannot come in string theory. In other words, the quantum correction should at least give us a potential like that. So this is the minima, which is the Minkowski, and this is the positive energy. So if I add quantum correction properly, we should be able to not only get this square root of lambda piece over here, we should also get a potential of this particular form in string theory. If we get it, then we are all done. So that should be the hope. And then the fluctuation around this particular so-called vacuum will produce the de Sitter solution and the corresponding fluctuations. Unfortunately, it seems that string theory may not allow a potential like that. What it allows appears to be this. So these are all Minkowski minima. So all minima are Minkowski with possible ADS minima. Of course, this dotted term has ADS minima also, so it can go deep in the negative direction. But turns out that there is also some tight constraint there. If the ADS minima are scale separated, then they do not appear also in this kind of potential. So it appears that despite the richness of string theory may not allow a potential of that particular form. And instead, the potential appears to be of this particular form with a lot of Minkowski minima or ADS minima. And the ADS minima are all non-scale separated. Question is, why is that? So that will be the basic discussion of my talk over here. To study this, we'll use M theory. You may immediately interrupt, saying that we are claiming to study de Sitter from M theory, but we know nothing of M theory except maybe the low energy dynamics. So how are we going to tackle that? The answer is, of course, true that we know nothing of the ultraviolet behavior of either string theory or M theory. And it will be insane to say that we know anything about the short distance behavior of these kind of theories. But we do know one thing for sure, is that no matter how complicated the short distance behavior of these theories are, no matter what kind of weird degrees of freedom are there at the short distance, the far ultraviolet dynamics are well defined without any pathologies. This is important for the consistency of this theory. We don't know what is the UV dynamics. We don't know what degrees of freedom are at short distances. We know absolutely nothing of what the short distance behavior is. But we know one thing for sure, that either in string theory or M theory, the short distance behavior have no pathologies. It's very well defined. We may not know anything about it, but it's very well defined dynamics. If this is not true, then there is nothing to work on actually. The whole string theory is based on that assumption that the short distance behavior is well defined. So how are we dealing with that? So what we do is that even though we don't know what is there in the far ultraviolet over here, we can integrate from lambda UV to this particular scale over here. And if we do that, an exact renormalization group procedure, if we are successful to do it, will tell us that all information over here in this little small shaded area where we'll study our physics over here, all information of the UV, no matter what crazy dynamics are there, what degrees of freedom are there, all information of the ultraviolet is not lost, and it's given by the coefficients of all the relevant, irrelevant, and marginal interaction of the massless states over here. You see the KK scale is very high. The string scale is higher, M-Planck scale is high, lambda cutoff is somewhere here. So in this particular here, there are all the massless states over here. And there is, so you can write all an exhaustive list of marginal, irrelevant, and relevant interaction over here. And the coefficients of these terms are important, and they carry all information of the UV dynamics over here. So that's the beauty of the renormalization group flow, that we never lose any information at any scale. Of course, the physics is different at different scale, but Wilsonian method, or more correctly, the exact renormalization procedure, tells us that at any given scale, all informations are there if we keep all marginal, relevant, irrelevant interactions. That's theory. So if you are stuck with this particular regime, and if you keep track of all these states over here, all the operators and all these things made up of massless thing, then if we know that the UV behavior is consistent, then we don't lose any information, and we can study in this particular regime. So most of our analysis, actually all of our analysis, will be in this little regime here. Well, as I said, of course, this means you have to keep track of all possible operators constructed from the massless degrees of freedom. This way, we lose no information of the ultraviolet, but the subtlety is that some of these massless states could be off-shell. So there's a long story of how to deal with off-shell state, and I'll come back to it at some point. Now, what does that mean? That means for a metric like this, so if I give a metric of like this in type 2B theory, for this thing to appear as a vacuum solution in type 2B theory, so let me just introduce you to various terms. So these are the 4 dimensions. This is the internal space over here. This is the internal space metric, which I have put some time dependence over here. And this metric is not necessarily a complex manifold. It's a compact manifold. It's not complex, neither Kähler nor Calabi-Yau manifold. This is the de Sitter solution over here in the flat slicing, so that T goes from -infinity to 0, and H is the warp factor, and lambda is the 4-dimensional cosmological constant. If you want this to be a solution, vacuum solution in type 2B theory, it's most easy to study from M theory, and if you uplift it to M theory, then the consistency condition for this particular metric to be a solution turns out to be this very simple equation over here. So note that this first term is flux term. So this is the, since M theory has only 3-form flux or 4-form fluxes over here, so this is the flux term over here. And this particular term is the brane and an anti-brane pieces over here. This is the so-called uplift of the orientifold plane over here. This is the cosmological constant over here, and this is the quantum term. Now imagine we have no quantum piece over here. Imagine we are given no quantum piece over here. The consistency condition says that this plus that is equal to 0. Now you see, this is all of the 3 terms are positive definite. If lambda is positive, all the 3 terms are positive definite. So if lambda is positive, in the absence of any quantum term, neither flux, nor brane, nor anti-brane, nor orientifold plane, or anything can ever give rise to a solution over here, because the only possible solution is that each of these terms individually are 0, because sum of the square. On the other hand, if lambda is negative, then you see, we don't need the quantum piece. There's always a solution possible. So even lambda equal to 0, there would be a solution, that the simplest solution. So lambda negative or 0, it's very easy to get in string theory. So that's the reason why ADS spaces are so easy to get in string theory. But de Sitter spaces is almost practically impossible with classical sources over here. People think that maybe O planes can help us, but actually you can also check that orientifold plane also does not help. So it appears that the only possible way a solution is there if sum of all the quantum pieces is a negative definite integer. This is a bit of a weird condition, which means it calls for some kind of hierarchy in a quantum series. which actually may sound like a good news, because if we can somehow allow some hierarchy and satisfy the above condition, we might get a de Sitter vacuum solution. And even better news, with time-dependent degrees of freedom, it appears that we can find some kind of hierarchy. So question is, what is stopping us to declare victory and finish the talk right away, saying that we can find a de Sitter vacuum solution? So we almost thought that it's possible. So we come so close to getting a de Sitter as a vacuum solution. But it turns out that we have made an assumption in this whole analysis. The assumption is exactly the quantum terms that I was talking about. Recall that when I said the quantum term, by the quantum term, I mean that since we are defining everything at the far infrared, this quantum term that I talked about, for which we want to see some hierarchy, they must have come from integrating out the high energy modes and heavy degrees of freedom, these series of quantum terms. Now comes the question, what if we could not integrate out these high energy degrees of freedom? Of course, if we can integrate it out.
Sorry, I apologize. Can I ask a quick question here?
Yes, please.
So when you talk about these quantum terms, are you talking about things like membrane instantons and worldsheet instantons?
Everything. We'll come back to instanton. You'll see. I will discuss everything. When we say quantum, it could be all kind of terms.
Okay, thanks.
Okay. Right now, I'm just talking about integrating out the high energy degrees of freedom over here. The question is that what if we could not integrate out these high energy degrees of freedom? So you might say that this is ridiculous. When could such a situation arise? It could arise in two specific cases: when there is no well-defined ultraviolet completion, or when the frequencies themselves are changing with respect to time. Now, we can clearly rule out the first one, because as I just told you that no matter how complicated the short distance behavior of string or M theory is, the UV is well-defined theory. So there is no problem with the ultraviolet. But the second is an issue now, actually, because one can easily check that the fluctuating frequency over a 4-dimensional de Sitter space, for here, example right over here, if you have a de Sitter's vacuum solution and you study the fluctuation, the way you do quantum field theory is that you find a vacuum and you study fluctuation and you integrate out this fluctuation to write an effective field theory at certain energy scale. One can show that the fluctuating frequencies, because the surrounding space is expanding slowly, the frequencies are actually changing with respect to time. Now, Wilsonian method is integrating out the high energy frequency. Now, as you start integrating out the high energy frequency, the frequencies themselves are changing with respect to time. So there is no meaning of integrating out process now. And it fails very badly. So there is no simple Wilsonian integration possible. You might immediately say, what about static patch? Everything could have been done on a static patch over here. In static patch, there should not be any problem. Unfortunately, for a few years, actually, I was thinking static patch is the way out of this thing. But it turns out that in the dynamics on a static patch is highly deceptive. So let me give you a cartoon example of this one. So imagine this is the static patch. I've just drawn a cartoon example. I'm not drawing the Penrose diagram. So these two black lines are the boundary of the static patch. And this is some high energy frequency from UV to IR. Now, clearly, you see that the frequency is not changing with time from UV to IR. So one might be able to integrate this frequency out. Okay. But please give a close attention to the top one and the bottom one. So an observer sitting here will see that the frequency is not changing with respect to time. He will integrate out this thing, will try to write an effective field theory. But what is really happening just outside the static patch is that you see the frequencies are changing because the time-like vector becomes space-like and so on and so forth outside the static patch. And if you use global coordinates, you can easily see this, that this frequency on the top and the frequency at the bottom are actually not the same. They are actually changing with respect to time. If you take a Fourier decomposition of the top and the bottom, you'll see that the frequencies are actually changing. But the observer in the static patch will have no clue that this is going on over here. And he will, by mistake, he will integrate out and he will try to write a theory, effective field theory in. Now you may say, okay, that's about, since the observer doesn't know, he doesn't have to worry about it. But this is, of course, wrong, because a static patch itself is an observer-dependent quantity. Unlike black hole, where the static patch is not observer-dependent, here it depends upon the observer. For example, a different observer with a slightly different static patch will notice this problem. And a somewhat similar observation Banks had a week ago. He found that there appears to be energy leakage in a static patch. So I communicated with him on that aspect of this. So he said that most of the analysis has been error because of that particular thing. So if you have time, you can look up this paper. It looks like a very interesting way to deal with that. He pointed out that similar problem. Moreover, it turns out that in a static patch, one can show that the dual type 2A coupling is greater than 1. So instanton series cannot also be made convergent. I'll come back to Alok just asked some question on that one. I'll come back to that issue a little bit later. You might think going to M theory helps. It actually does not help. One can check all of these things. So all in all, it seems that static patch is not a way out of this particular mess. So you may ask, how did people deal with this thing? This cannot be a new thing. People must have observed all of these things before. And in fact, people did observe it actually. Quite a sizable population of GR people did observe that thing. And I know that there are three ways this was handled. One is that you ignore it and continue with the static patch story, or just do ADS CFT and forget that nature has positive lambda. The second one is use open quantum field theory, where energy is not conserved, and use Markovian techniques. Or third, propose a Transplanckian censorship criteria to block the temporarily varying UV mode to escape the horizon. The second one, which is called the open quantum field theory, I'm sure you know what it is. It's actually a very interesting kind of theory. It was first proposed by Feynman and Vernon. It deals with the way things are done here is that you separate some relevant degrees of freedom from an environment, and the relevant degrees of freedom lose energies to this environment, and you study this dynamics of these relevant degrees of freedom. But since there is no simple Hamiltonian or Lagrangian description, you have to use some kind of Markovian process to do this. But the assumption is that you should be able to separate it. But overall, the whole system with the environment and that with the relevant degrees of freedom should have a well-defined effective field theory, but you can separate that thing and study the dynamics. So this is called an open quantum field theory. The problem with this picture is when we try to use it in string theory. See, in an ultraviolet complete theory like string theory, there appears to be no simple way by which we can make this clear distinction between what is relevant degrees of freedom and what is an environment. And even if we do that, we do know that we still have to define a well-defined effective field theory for the whole system. Otherwise, things will not make sense. So this whole process of using open quantum field theory and string theory, as far as I know, has not been very successful. For the third case, which is the Transplanckian censorship, now that arose, that was mostly started by Brandenberger and Martin. They observed that since they did it for GR, and we know that the ultraviolet description of GR is not good. So they wanted to censor those UV modes because, as I just told you, if you start with a UV mode, it will become IR. But if the UV mode is not well defined, when it becomes IR, it will bring all the problems of UV to large distances. So they said that this problem should not appear in our spacetime or in our energy scale. So they put a censorship. They said that temporal evolution should be such that these UV mode can never cross the horizon. So they put a temporal bound on such evolution. This way, they kind of ruled out that long-lived inflation cannot happen in GR and so on and so forth. But In string theory, we know that there is no problem with ultraviolet. So no matter what degrees of freedom exist there is no pathologies from the UV mode. So as such, there doesn't make sense of censoring the UV mode. And there should not be any censor. So it turns out that this temporal bound that these people have been saying appears from a different issue in string theory. If so, from demanding convergent instant on series and so on. I'll come back to this particular thing. All in all, it says that all the three arguments that I gave above, it's unsatisfactory to deal with the situation like that. This is where de Sitter as an excited state over supersymmetric Minkowski background appears. So that's how we eventually argued this the case. So do you have any question? All right. So here is the claim. The claim is that in string theory, there is no potential like this. It's unlikely there will be a potential like that. The bottom part is the Minkowski and this is the positive energy one. Instead, it appears that string theory can only have a potential like this with dotted term. This dot 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 has ADS minima, which are non-scale separated. Now, I know that the Harvard group had also come to similar conclusion, but their argument, to be honest, I do not understand completely how they are coming to this so-called swampland criteria. So I'll not talk about those way of arguing over here. I know Van Riet and all also came to similar conclusion. So it appears that despite the richness of string theory does not have many things which people thought string theory can have everything. It does not actually have. So this is the claim. This is the main claim of that there is only a potential like that with multiple Minkowski minima. On the other hand, de Sitter excited state cannot be a coherent state. It's wrong to say that de Sitter is a coherent state, and many paper in the past have claimed that, well, some paper in the past have claimed that de Sitter is a coherent state. It cannot be a coherent state because over any Minkowski minima, because we expect the de Sitter state to have all the quantum corrections somehow inbuilt in it. Coherent state is classical. So if you create a coherent state, it's going to clash with that. On the other hand, coherent state is just a fancy way, as you know, if you have a potential like that, and if there is a de Sitter minima over here, that de Sitter minima from the Minkowski point of view will appear as a coherent state by Bogoliubov transformation. So coherent state is actually a fancy way of saying that there exists a nearby de Sitter minimum. So coherent state, de Sitter cannot be a coherent state. What it could be is that it's a more non-trivial excited state, which we called it the Glauber-Sudarshan state, which is constructed by acting some kind of displacement operator on an interacting vacuum of the theory. This is the interacting vacuum, not over any Minkowski or anything. It's the interacting vacuum over the whole system here in the full potential that I showed you. And D is a non-unitary displacement operator. So it differs from coherent state in multiple ways. First of all, it's not a free vacuum. It's an interacting vacuum. It's also not a interacting vacuum over any, it's an interacting vacuum over the whole potential that I showed you the potential before. With multiple Minkowski and ADS minima. And D is a non-unitary displacement operator, which is again different from coherent state, where D is a unitary displacement operator in coherent state.
I have a question.
Yes, please.
So
Please.
are you ignoring the flux vacua of the this? I mean that originate in string theory in order to take care of the finite cosmological constant scenario?
No, I'm not ignoring any flux vacua. Actually, when I said that de Sitter vacuum solution does not exist, those were actually related to the flux compactification and all. Like.
Yeah, but it's well known that this landscape people, they do have these de Sitter vacua. So
actually, no, none of these are actually correct. None of these satisfy these condition, and under careful scrutiny, it turns out that they do not actually are consistent. They are not consistent.
So you mean KKLT and things of that kind are not consistent?
I don't want to put words on that, but let's not say that. I think so. I mean, you can see the argument that Buffer gave and other people gave on that.
Okay.
I'm not the one to say that, of course. I mean, this was already proposed by Van Riet and Danielson, Kumrun, Baffa, Guri, and others. So they actually wrote a paper which I think let's not talk about that one. I don't know. Let's put it this way. I don't know about KKLT. Let's put it this way. But I believe that none of these vacuum are. Let me give you a quick answer why there is an issue over here. KKLT vacua, if you see that they have a superpotential term, then they have an anti-D3 brane term, right? And they put an anti-D3 brane term to uplift. Anti-D3 can break supersymmetry, but cannot. They can break supersymmetry and can make an ADS space to a non-ADS space. But an anti-D3 brane can never be able to take an anti-de Sitter space and flip the sign of the cosmological constant. Anti-brane cannot change the cosmological constant of any theory. Orientifold plane also cannot change the cosmological constant of the theory. You can break supersymmetry in your theory, but you cannot change the cosmological constant.
Okay.
Yeah, it's a little bit tricky thing, and it's a bit of a point of conflict. I mean, of course, some people agree, some people don't agree, but if a careful scrutiny will tell you that this is how it is going here. So we have assumed that the vacuum is non-degenerate, and there is an energy gap between the first excited state and the vacuum. The vacuum is the interacting vacuum, that omega over the Minkowski, over this whole complicated potential. So I make two assumptions when I construct this particular thing over here. This particular thing, this omega vacuum, when I say I've just assumed that it's non-degenerate and there is an energy gap between the first excited state and the vacuum. Now, how do I extract the metric of the space-time from this GS state? So we'll use this formula over here. So we'll do the usual calculation, taking the metric operator and sandwich between the two GS state, and take this divided by that. So question is, how does that work over a given Minkowski minima? Okay, so you choose this potential. In this potential, there is a interacting vacuum of this theory, which is non-degenerate for this whole potential. And now you choose your favorite Minkowski minima where we want to live. So this is, imagine, this is the point where we want to live over here. And I'll call this minima as 0, min 1, this over here. And now I express this 0, min 1 as a linear combination of these eigenstates of this exact vacuum, which actually I don't know, but I can write it symbolically in this way. So you may say that this contains no information because when we don't know omega, we don't know n, so we don't know how to connect 0 minimum with omega. But we do know one trick by which people have done this is to hit this both left-hand side by e raised power of minus I h dot. H dot is the total Hamiltonian times t, which I can define over a Minkowski space or over the whole space over here. And then take t to infinity in a slightly imaginary direction. If you do that, it will kill off all the states n. It easily kills off this. And then you can relate omega with 0 minimum over here. You can do this thing. That's the standard trick people use. Now, you might worry that we have no idea what the total Hamiltonian is. Of course, that I agree with you. But slowly we'll see that we can actually quantify this Hamiltonian also. So if you plug that thing over here, take the same trick. So you see omega, sigma is defined by d dagger omega, metric, and so on and so forth. And you plug this, replace this omega by 0 minimum over here and this, and use e raised power minus I h t and take t to infinity 1 minus I epsilon. You can convert this thing to a path integral of this particular form. So that's how the expectation value of a metric can be replaced by a path integral with this particular thing over here. So this is all the measure of the path integral, and this is the action, total action, d dagger d, and the metric, and so on and so forth. In the M theory uplift of this type 2B scenario. Note that we haven't yet specified with what S total is. Now, if the above works, then we are claiming something interesting. We are saying that de Sitter metric is an emergent concept. And S total should get contribution from the kinetic term, the complete series of perturbative correction, non-perturbative correction, non-local correction, gauge fixing term for the Popov ghost, and everything else. Now, that's a very complicated business. So to simplify this for this particular talk, I will take a simple scalar field model to show you all of these things. In the scalar field model, you can avoid the Faddeev-Popov ghost, and you can avoid the derivative ghost by taking polynomial interaction in your theory. But we still have to worry about the non-perturbative and the non-local interactions. Moreover, you might ask, since at the far infrared M theory is known to be a local theory, what does it mean to have non-local interaction? So I'll clarify all of these things right now. But before I go ahead, do you have any questions?
Keshav, I had a couple of questions. If I may.
Please.
Pretty dumb questions, but I still would venture to ask them. The first thing is that you're dealing with time-dependent backgrounds. So I would imagine.
Say that again.
Hello. Yeah. So you're dealing with time-dependent backgrounds. Your ansatz assumes a time-dependent background.
No. It's over a Minkowski, completely Minkowski time-independent background. It's over this background. It's completely independent, time-independent background where you can do a Wilsonian integration without any problem. What will happen is that using this trick, you can create a state over here. That state will have an emergent metric of this particular form. That emergent metric will become time-dependent.
Oh, I see. Okay. I see. Because there was an ansatz made earlier, which was a
right. So that's we avoid that problem of this. Now, since you are doing everything over a time-independent background and over localized over a Minkowski minimum, we create a new state inside that theory from this interaction and take a expectation value of the metric operator in this state, so that the de Sitter, the time-dependent de Sitter kind of background appears as an emergent quantity.
So how would the time dependence appear from this definition of G mu sigma?
You can see soon. I'll explain to you.
Okay, and my last dumb question is, what is meant by this operator D, the non-unitary D? Call it a displacement operator.
I will also explain to you. I will also give an example how this can be quantified.
Okay, great. Thank you.
Any other question?
Yeah, I have another question.
Yes, please.
Is the Glauber-Sudarshan state an eigenstate of the metric operator?
No.
But I mean,
it's not an eigenstate of coherent state is an eigenstate of, but it is not an eigenstate as such.
Yeah, but when you act by the metric on the vacuum, or rather the Glauber-Sudarshan state, don't you expect to get back the metric that we see in nature?
We do, but if you hold on, I will show you exactly how we get the emergent metric. Do you see this formula of the path integral?
Yes.
Okay. So you act a G. Imagine D was not there. This would be 0 because the 1-point function would vanish. But D is there, so somehow because of the D, this 1-point function does not vanish. The 1-point function does not vanish and give rise to something here. That something should eventually be the metric that we want to see for the de Sitter space. How it works out, we will figure that out soon.
Okay.
But it's not an eigenstate in the sense of coherent state. It's not exactly a coherent state. So now let's question is, first thing first, how do we quantify the non-perturbative terms? Now, this is where some magical thing happens. Remember, we said that once we do all order infrared integration over a Minkowski minimum, it turns out that when we do such Wilsonian integration, you get a perturbative series over here. And the perturbative series is actually asymptotic, which means that the perturbative series blows up when we do this calculation. And what the non-perturbative effect means is that the non-perturbative effect are put in this problem to avoid this asymptotic behavior of the perturbative series. Now, in the language of this multi-minimum Minkowski potential, these non-perturbative effects come from both real and complex instantons, because you remember that the potential had multiple dips over here. And so there could be, if you choose any Minkowski minimum, there could be tunneling around all of these surrounding minima, and therefore you can see the behavior as real and complex instantons over here, which means that given a Minkowski minimum, S total can be expressed as a trans series. This literally means that the S total, which I told you, which I could not quantify at the beginning, now I can quantify it. This S total, which I can find it at a given point in the Minkowski minima, can be rewritten as a sum over all the instanton saddle, you can see, and then the corresponding fluctuation determinant. So in other words, S total should take this particular form. It should be a instanton saddle over here, and then there will be this fluctuation determinant. So it will be no instanton, then fluctuation, 1 instanton, fluctuation determinant, 2 instanton, 3 instanton, so on, and an infinite number of instanton over here. So this is called a trans series. You see, there is no more this perturbative interaction at all. It's a completely non-perturbative form, and such a form, this guy over here, actually is no longer asymptotic. It does not blow up, and it behaves very well over here. And the thing is that all quantum field theory should be hopefully be written in this particular form. Like lambda phi 4 theory, we should actually write it in this particular form, because if you take lambda phi 4 theory, that's not going to work at some order of perturbation theory. So it's better to write it in this particular way. So this is a more modern understanding of quantum field theory, that there is actually no meaning of perturbation theory in quantum field theory. It's so this is called the resurgence method of resurgence.
So sorry, Keshav, these what you call as GN S part N comma M. So I mean, they are basically arising. So what you call as fluctuation determinants. These are basically bosonic and fermionic Pfaffians, right?
Yes, that's why it's a fluctuation determinant. Yes.
So,
but the subtlety is that usually people do real instanton. Now you can also take complex instanton, because it's the complex turning point of that also to be taken into account. So that makes the resurgence a little more richer than what people knew about only with the real instantons.
And that is probably also more desirable, because you'd always be interested in looking at a complexified Taylor modulus, for example, or in the context of let's say N2 brain instantons, you'd be complexifying the volume with the 3-form potential. So you usually always expect something complex, right? So what I'm trying to get at is that these Pfaffians are basically they contain the content of the operator, right? I mean the Dirac operator or the Klein-Gordon operator in the action.
I'll show you exactly how it comes about in one bosonic case.
Okay. All right.
Okay. How am I doing with time? Am I doing okay with time?
Yeah, you feel free to go on. You still have, I mean, we are not very strict with time, so if you run over time, that's fine.
Okay, great. Thank you very much. That was all right. So as I explained, yes, sorry.
So when you are saying the entire action is written in terms of fluctuation determinants, these fluctuation determinants presumably come from integrating out fields. I mean, they are essentially quantum terms, right?
Yes, exactly. If you give me a moment, I will quantify it for you. I will quantify it for you exactly how. I'll give you a particular form of such fluctuation determinant.
No, my question was what happens to the initial kinetic term?
Oh, it is there. It is there. It is there. I just forgot to write it. I forgot to write it. I just forgot to write it, but there will be plus initial kinetic term. All right. So now, since we took a simple scalar field, we do not see the GS effect. And in particular, the instanton d-brane saddle, we don't see. But if you take the GS, you'll also see the instanton saddle. And if you remember, this is how Shankar came to the conclusion that string theory has a d-brane. He actually did this resurgent trans series calculation, and he found that, of course, string theory is asymptotic. And from there, he argued that there should be d-branes in the theory. But here we'll only see non-perturbative effect associated with M-Planck. If you're courageous enough, then we can do the GS and you will see the d-brane effect also. So here is the conclusion. First conclusion, for a given Minkowski minimum, out of these multiple Minkowski minimum, we choose our favorite Minkowski minimum where we want to live. We see that the effective action is given in terms of an infinite series of instanton saddles accompanied by a corresponding fluctuation determinant. Again, in full string theory, if you are able to do this, then there should be a contribution from d-brane and other possible GS-related instanton saddle. These d-brane instantons should reproduce Shankar's original motivation for introducing d-brane and so on. And the good thing about it is that this asymptotic nature of the perturbative theory provides a reason why nature has non-perturbative effect. In the beginning, people studied non-perturbative effect as all kind of tunneling, but now we know why nature has non-perturbative effect. Nature has non-perturbative effect just to keep track of the fact that the perturbative series blows up and so on and so forth. Now, it turns out that even with scalar degrees of freedom, we can quantify the story further. So let's see how far we can get. First, you may have noticed that we do not have any on-shell degrees of freedom in our analysis because everything emerges from a path integral computation. So everything is actually an off-shell computation. As an example, remember, I tried to initially show that this cannot appear as a vacuum solution. So if I lift this guy to M theory, I could equivalently say that this particular metric cannot appear as a vacuum solution. Note that in M theory, I choose 3 of the direction and I put it over here. The coefficient changes slightly. This internal metric over here remains internal metric, except that the coefficient changes slightly. And one of the direction of 3 and the 11 direction combine together to form a torus and picks up a new coefficient over here. This is simply an uplift of this solution to M theory. But unfortunately, as we talked about this, such a solution does not appear as cannot appear as a vacuum solution. So how do we realize this solution? So here is the answer, is that the on-shell configuration, which is an expectation value, so that expectation value of G mu should be equal to this guy. Expectation value of GAB, which is the 3 and the 11 direction, should look like that. And expectation value of the GMN should look like this. So this is the claim. So here is an example how an off-shell computation creates emergent on-shell components in string theory. So it goes to show that there is nothing classical in our analysis. On the other hand, we also have cross term in the metric. You see that our metric doesn't have, for example, there is no G0M or G03 or G011 or GM3, M11, so on. We don't have those cross terms over here. So those are actually real off-shell component, and they should satisfy that the expectation value of such G mu M, G mu A, or GMA should be 0. They are called off-shell because the actual component of G mu M, G mu A, G A are actually non-zero. So if you put them in the path integral, they should give you an answer 0, which turns out to be not very hard to show that it works out fine. So question is that, so this is what we should expect from our analysis. If we can successfully do this computation of path integral, we should be able to equate it to this particular thing. Okay, so that the whole spacetime in either 2B or M theory is an emergent quantity. Now you may also ask, how long do such emergent quantities survive? Well, I don't want to go into too much detail. It turns out that the answer is that this emergent state only survives for this particular interval of time from -1 over square root of lambda to 0, because we are taking the flat slicing from -infinity to 0, but these states only survives for a short period of time. Interestingly, this answer is exactly the same answer that Brandenberger, Waffa, and all have predicted from their analysis, and Diwali and company have predicted from their analysis using coherent state. But since our analysis shows that it's neither a coherent state nor has Transplanckian problems, so it's interesting that we are getting similar answer. But I don't want to make further comment on that connection to their answer. But we all of us agree that these states survive for a short period of time. So there is no long-lived de Sitter, emergent de Sitter state possible in string theory. Now, question is, you may wonder what equation of motion those emergent components satisfy. Well, you may have already figured it out. They are, of course, the Schwinger-Dyson equation, and they take this particular form. Del S total, remember that S total I told you made up of all this trans series over G mu nu, you take the whole thing expectation value, you should be equal to this thing. So this is the Schwinger-Dyson equation that these states satisfy over here. Now two questions arise. Can we bring the equation into some useful format? And how are we dealing with those off-shell components that I talked about before? So to answer this, I will take a very simple scalar field model with two fields. One we'll call it on-shell field phi that represent these so-called on-shell component G mu nu, Gm, and Gab, which appear in the classical or in the background metric. And the off-shell field phi, which represent G mu m, G mu a, Gam, whose expectation value are all 0. Okay, so I write a S total in this particular form over here, which is this particular thing. And I will rewrite this in the form of trans series very soon. But for the time being, I write it like that. So you see, this is a perturbative interaction over here. This whole perturbative interaction should be replaced by this whole trans series. And these are the kinetic term that somebody was just, Somnath, I guess, was asking. And here is, I wrote it as the perturbative series, but eventually I'll remove this perturbative series and show you how the trans series appear over here. And these are made up of these on-shell scalar and some off-shell field over here. And there's the interaction over here. And C is the coefficient over here. And these are
Keshav, just one thing. So is the off-shell metric flat? Is it Minkowskian?
Off-shell metric is, the off-shell components of the metric is all 0. The expectation value of G mu m is 0. Only the expectation value of G mu nu is what we want, Gmn is what we want, and Gab is what we want. And all the off-shell component, despite the fact that G mu m, G mu a, and Gam are non-zero, if you put them in the path integral and you integrate, one can show that they actually vanish, showing that their expectation value are, their emergent quantity is 0.
I mean, what I'm trying to understand is that what is the metric for this action that you've written?
Metric for the what?
For the action, the 11D action that you've just, in the example that you're just discussing, which has both
okay. This one I choose a simple flat metric over here. This one I choose a simple flat metric scalar field. So what I'm doing is that I'm identifying this. So I'm identifying this phi with one of these G mu nu, Gmn, and Gab. Okay. So if you really want to write this, phi box phi is nothing but a square root of Gr reduced to this particular form, phi box phi. Okay.
And if it is a flat metric, that is not 0 still.
Yeah, that's not 0. Yeah, that's still not 0. Yeah. So what I'm doing is that I'm replacing the G mu nu, Gme by scalar degrees of freedom, G mu m, G, just for simplicity. Otherwise, this whole 11D has to be replaced by square root of G11, and then you have to use these components and all this metric component and so on and so forth. But for simplicity, if we ignore all of these things and simply take a scalar field theory with phi as one scalar and another phi as another scalar, then we can write an action of this particular form. And we can study what, if I want to study an expectation value of this curly phi over here, how does it look like in the path integral?
But as per your proposal, strictly speaking, shouldn't the following be true, that the var phi should not appear in the action? The on-shell, the var phi, which represents the on-shell metric, should not appear in the starting action. It should appear as what you obtain via your prescription.
No, wait. These, if you put it in the action and if you view it as an operator, okay, if you view these, put it as an action and view them as an operator, then the claim is that expectation value of the phi operator is what we observe, and expectation value of small, that let's call it var phi and this is called phi. Expectation value of var phi will be equal to what answer we get, and expectation value of small phi over here should be 0 in the path integral analysis. But nobody stops us to have all the fields in the path integral, right? In the action, you can have everything.
Okay.
See, when we say that everything, it's a path integral, everything we want should be there. It's the final expectation value as an emergent quantity, whether it exists or it does not exist.
Okay, good. Thank you. Yeah,
okay.
Thanks.
You are saying that you are getting these terms from the root GR term, right?
Yes.
Root GR term would also have some interactions between the phi's.
Absolutely.
So, I mean, you're working in what limit are they negligible?
I should actually, so the kinetic term would come about it.
That's the third term.
No,
Sorry.
third term has a different implant dependence. Can't be the third term.
Well, you're summing over all K.
I'm summing over all Ks.
Okay. I see.
So you see, I'm summing over all Ks and also L, all N or all M. So everything I'm plugged it like that. Okay. The reason I don't want to use an actual metric is because, when you put it, I mean, it all looks innocent here over here. But once you put them in the path integral, then things become a little bit crazy because Faddeev-Popov ghost has to be put in, derivative ghost have to be put in, and so on and so on. So things get a little bit weird there. So once you put Faddeev-Popov ghost in the theory, then the calculation becomes just goes beyond control. So if you just stick with simple scalar field, then we can avoid at least this, but still you have to use derivative ghost over here.
K ranges over what values?
K
What
K
value?
ranges over, in this case, Ks are all positive from 0 to infinity.
0 to infinity. Okay, then.
I'm not taking negative. K is not negative. I'm not taking K to be negative, if that's your question.
The interaction terms will come from K equals 1, right?
Interaction term will come from K equal to 1.
Okay.
Yeah. Is it clear now?
Yes, but you should include the implant to 2K minus 2 inside the sum. I mean, it's outside.
Yes,
So
due to some reason, some crazily it has gone outside. It should be inside the thing, absolutely. Thank you for noticing. Okay, so that's the kind of action I'm taking. Just I'll show you with this thing how you can do a calculation. The actual calculation is, of course, much weird. So what is the Schwinger-Dyson equation for this kind of action? If you do that, well, it turns out that the Schwinger-Dyson equation takes this particular form. You can see how this part is thing, S1 and S2, if you recognize this, S1 is this one, S2 is a combination of both phi and phi, S1 is only with the on-shell field over here. So that's how the Schwinger-Dyson equation looks like. You may say that there is nothing, it's just putting some bunch of stuff together. But if you carefully rearrange this particular equation, if you carefully rearrange it, then this equation looks like that. So now you see this rearrangement is something interesting. So you see, this is the measure of the on-shell field, and these are all the on-shell field over here, and this is the off-shell field over here. The second term also, left-hand side has all the on-shell fields over here, and then there is a off-shell field over here. And again, the same story over here. Now, both on-shell and off-shell fields are massless. And in a path integral, if you integrate out the massless fields over here, we know that we get a non-local action over here. So that's how this non-local action appears. But now the non-local action completely is given in terms of the on-shell field. So what is the moral of the story? The moral of the story is that if a theory has both on-shell and off-shell fields, then we can simply write everything in the language of on-shell fields, but you have to add the non-local pieces over here in this particular way, so that now the equation of motion takes this particular form. Okay, so now no information of the off-shell field is required anymore, and the theory can be completely written in terms of on-shell fields over here. Well, of course, this is a well-known fact about quantum field theory, where D is given by that particular thing. And one can actually massage this over here. You can take the box outside and put this, and you can write this equation as an equation of box of this. So this looks more and more closer to an equation of motion for a on-shell field over here, except that the equation of motion is not for on-shell field phi. Equation of motion is an equation of motion for an expectation value of phi. So as though all the equation of motion is replaced by an equation of motion for a expectation value. And that's what exactly Schwinger-Dyson equation does for this. Now you may ask how it's all related to the trans-series example that I talked about here. So now let me give you an actual detail of that thing. Let me first define a perturbative operator made up of on-shell fields over here. So remember the metric we took in M theory. It turns out that if you take the metric as I wrote over here, there are 60 different components of the curvature tensor modulo their permutations. And there are almost 40 different flux factors over here. They're all on-shell here. And this is a complete set of perturbative operator you can write in your theory. You don't have to worry about other off-shell components. And then Li and I goes from all possible combinations. So there is an infinite number of possible interactions you can take into account over here. And the coefficient is CNL. Okay, so
Sorry,
for
Keshav,
example,
just one, I apologize, just one question. Are you assuming supersymmetry?
yes.
So that would probably help you in reducing
Yes,
considerably
I know.
the number of terms.
Yes, because the Minkowski, so here is what happens. The minimum is supersymmetric Minkowski, so the 0-point energy does not contribute, but the emergent state breaks supersymmetry. So it's very interesting that everything is supersymmetric in analysis. So the 0-point energy does not contribute, and you can do all this calculation over here. And once you create an expectation value of the metric and the state we create over here, that state actually breaks supersymmetry. So it's a spontaneous breaking of supersymmetry. Supersymmetry is spontaneously broken.
But without including the fermions, how do you see the breaking of supersymmetry?
We don't. You have to use the fermion too. So
okay. Oh, I see.
The actual answer is this curvature can be rewritten as a bosonic plus a fermionic piece. It's a little more mess over there.
Okay.
Thanks for noticing. Yes. Fermions are essential, and in my more upcoming paper, you will see all the details about how fermions are introduced. So this was also observed by Diwali et al. They also observed that supersymmetry is broken spontaneously. But again, they were taking coherent states. We are taking something else. And all right. So the equation that we used in the Schwinger-Dyson. So if you take this particular thing, so the action that we use in the Schwinger-Dyson equation is now this. So this is the actual action that you were asking at the beginning. So in M theory, the kind of action that we now expect at that far infrared will look like the kinetic piece, the flux, and this usual piece. And now you see the second piece over here. The second piece is given by e to the power of, the sum is over s equal to 0 to infinity. S equal to 0, this whole thing goes away. And it's given in terms of this fluctuation over here. S equal to 1, you have this series. So you see, it's again a instanton-like saddle over here, and then there is a fluctuation determinant, except that the instanton saddle is given by this whole complicated series over here, e to the power of that, and then there is a fluctuation. But the coefficients are different over here. Okay. So again, for the non-local piece also, same story happens. There is a saddle over here, and then there is a fluctuation determinant containing both local and non-local fluctuations over here. So the moral of the story is that the total action, as one expected, as predicted by all these gang of people who have been doing resurgence and all, matches with what we have been saying, that it has the kinetic piece over here. And then there is no more perturbative interaction in the theory. Instead, it becomes a trans series. But now there is a trans series for the non-local pieces over here also, both local and non-local pieces over here. Now we are not taking, so if you, and you can show that now that we are taking everything over here, you can see that there are pieces over here, which we showed in our recent paper, has the D brain also and NS brain also hidden secretly inside that. So we did find D brains and NS brains in this kind of setup. So this is the most exhaustive way you can write all of these things over here. So it will contain D brain and D brain or M5 brain, M brain instanton will be there. Similarly, non-local pieces over here. Okay.
Another question, like
Yes.
These implang to the implang for 8 dimensions, implang for 11 dimensions, implang from 9 dimensions. How do they, I mean, are they large or small, or how do they compare with each other, so that, I mean, you can ignore some of the terms and work with the rest?
Yes, yes. It's a very good question. Right now, we are not ignoring anything. We keep everything, and we are not putting any hierarchy over here. But remember, the energy scale is between mu and Ki. I remember in the beginning, I showed you the energy scale. So that energy scale can be used to quantify. But the thing is that we cannot ignore anything right now here, as you will soon see why I'm saying this particular thing. That it's a good idea not to ignore anything right now, not to put any constraint, is that we can, because since the perturbation theory itself is asymptotic, it's not a good idea to ignore anything at this stage. For example, if you have lambda 5 to the power of 4 and lambda 5 to the lambda 1, 5 to the power of 4, lambda 2, 5 to the power of 6, you have terms like that, then one might sometimes say that you ignore the irrelevant operators and so on and so forth. But that's because we are not considering the fact that the theory actually has asymptotic behavior. If the theory has asymptotic behavior, it's not a good idea to ignore anything at this stage. And you will see why I'm not ignored anything over here. Very soon you will see. Okay, so this whole asymptotic nature of perturbation theory has created a big problem, and not a big problem, has completely changed the way we do quantum field theory nowadays. Because in the beginning, people used to teach lambda 5-4 theory and we are done. But now we know lambda 5-4 theory is not so good. It's based on perturbation theory, and perturbation theory is bad in quantum field theory. So things have to be changed a little bit. Anyway, let's not get into that thing.
So, Keshav, when you say that the M-brain terms have not been added, what you mean is things like the Birkhoff-Seskin-Townsend M3 brain action, or whatever the M5 brain action, if they were known, they have not been added to the story.
Yes, yes. Because we don't know the world volume theory on that one, so I did not add this thing.
I see.
Now, I'll just show you the equation of motion just for fun. We're not going to do anything on that. And this is what Pradeep and I decided. So this is how the equation of motion looks like. This is R mu nu minus half G mu nu R. First term may be familiar, but except that it's R mu nu of emergent quantity. Half of G mu nu, but G mu nu is replaced by this emergent expectation value. So everything is in terms of expectation value, you see. So this is just for fun. We are not going to use this thing. So that's the reason I do not want to deal with an actual metric and so on. And main reason of dealing with scalar field theory is to avoid this kind of crazy equation of motion. However, I haven't told you how the instanton appears. I've been just talking about how instanton thing, but I haven't explicitly shown you how the instanton appears. So let me just show you how this thing appears. And that is the last part of this talk. It turns out that I've been saying everything as trans series all the way. But this whole trans series relies on our ability to perform a Borel resummation. How do we justify this? All right, let's do that. We take again a scalar field action of this particular form. This is the scalar field action. Now I'm ignoring the non-local pieces over here. And I've just put a lambda phi 4 theory over here. I should replace this by a trans series over here, but right now let's just keep the lambda phi 4 theory. So this is the lambda phi 4 theory, and this is how I define D. D, somebody was asking, how do you define D? The simplest way to define D is a sigma phi over here. And this is the S total I've taken. Okay, so I'll take this simple model and I'll calculate an expectation value of phi in this model. I'll show you how the trans series appear and so on and so forth, so that you can map to whatever we said before in a more concrete way. So everything what I said can be concretely shown. I can show you in this scalar field example. So that's the famous lambda phi 4 theory. Now, we can identify this phi by, say, one of the on-shell component G00. If you want to map it to what we have been saying, is as though we are taking phi to be one of the G00. Of course, I'm not so careful because there should be a derivative over here to actually map it to G00, but just for an example, this is the case. This means we expect that, what do we expect? That if I can successfully calculate expectation value of phi, which means I should be able to calculate, which I should be able to map to G00. And I know that expectation value of G00 is, this is the answer that I expect. As I told you before, if you want to actually reproduce a de Sitter kind of state as an emergent quantity. So I'll do this computation on the left-hand side of phi, and then I'll map, and I'll show you how this solution can map to this particular result over here. And this way we might be able to also quantify this sigma. So let's just do this calculation. So I take the value of expectation value of phi and I put it inside the path integral. So here is how I put in the path integral. So this is the measure of the path integral. This is the kinetic piece. A is the propagator. So this is the kinetic piece, phi square. And remember, there was a linear term dd dagger that goes inside and make it into a square like that. And that is the interaction piece I have expanded as a Taylor series over here. And that's the source term phi. So that's the computation of the path integral. And I kept like that, 1 plus g square and so on and so forth. So I leave it on this particular thing. And I'll soon show you that there is, we cannot ignore any of the terms. So we have to keep all the term over here. Okay, so that is the form of the path integral. So it's explicitly written like that. AK is given by k squared by V. V is the volume of the space. K lies between infrared and so this is the small energy range in which k is there. We have ignored many subtleties. For example, I haven't explained to you how the denominator of the path integral looks like, but those are not very important. Now at nth order, so let's go to the nth order, 1 plus g squared. Let's go to the nth order. At nth order, you see this is the measure. And remember, as we know in path integral, the measures have momentum k, the kinetic term has momentum k prime, the interaction has a momentum k tilde, and the source has a momentum k hat. And in the path integral, we take all pieces to different momentum, and then we compare and how to make the whole thing non-zero. So this is the expectation value of phi over here. Let's go to the nth piece. The nth piece will look like g to the power of n coming from here, 4 factorial to the power of n coming from here. There's a factor of volume over here, v to the power of 4. It will be v to the power of 4n. And there is a 1 over v over here, 4 over 4, v to the power of 4n plus 1. And then 1 by n factorial coming from the Taylor expansion. And then this is the phi k1 plus phi k2 up to this to the power of 4n. So this is the nth order. And then there's the source term. So now for some of the rules of the game. Now, because of the volume factor, the most dominant term would be the one where all the 4n minus 1 momentum are different, with only one of the interaction momentum will match with the source momentum. Okay. If you want to get an answer out of that one, then if you expand it to the power of 4n, so there will be 4n momenta over here. All the 4n minus 1 momentum has to be different to be the most dominant diagram, and one of the momentum should match with the source momentum. Otherwise, the diagram will be subdominant. Now, if all the 4n momentum are different from the source momentum, such diagrams will be eliminated by the denominator of the path integral. This is like the vacuum bubble story. However, any two of the interaction vertex could have the same momentum and be different from the source momentum. But then no other vertices could have the same momentum as the source, otherwise they will be suppressed by the volume factor. If more than two vertices have the same momentum, then the amplitude will be suppressed by the volume factor and become subdominant diagram. So these are the rules of the game. And needless to say, this is a new kind of quantum field theory computation because we are using shifted vacuum. This also keeps 1-point function non-zero. So it's a new kind of quantum field theory we are doing. And we call those diagrams as the nodal diagrams. And one can study those nodal diagrams using these kind of rules, which are different from the Feynman diagram, Feynman rules over here. But I won't have time to tell you more about these nodal diagrams. We discussed this in one of our previous paper. Now, what happens at the nth order? At the nth order, you see that the diagram grows like that. 4n factorial, g to the power of n, n factorial. So you see the diagram is asymptotic. As I predicted to you, the diagrams become bad as we go to higher n. Even though g is much, much smaller than 1, you see the diagram become bad because they show a factorial growth. But this is not the usual Borel growth. Borel growth is if there was n factorial. This kind of growth is called a Gevrey growth. And if you compare this somewhat similar answer Shankar had in his paper many years ago. But we see now that the diagrams are actually bad. That's the reason perturbation theory is bad. That this, as n goes to infinity, even though g is arbitrarily small, this is going to blow up. So now if you take care of these things, so this is how the diagram grows up. So now you go back to the diagram and you see that at nth point, this diagram grows in this particular way over here. So let's go to the nth thing and integrate out the whole thing. And let's see how this nth integral looks like. After you take care of various subtleties over here, at the nth order, the growth is like that, g to the power of n, 2n factorial, a to the power of n, where a is defined by some particular series over here. So you see, this is how the diagram become bad. That's the reason you cannot ignore anything in the perturbation theory. If you ignore and you cut anything in the perturbation theory, it's not going to work because perturbation theory is actually not good. And here you clearly see that at order n, there is some value of n in which it's bigger. Even though g is very, very small, this diagram is actually blowing up. So what do we do when certain things blows up like that? So you, instead of summing over, you cannot sum in the usual way. You have to Borel resum the whole thing. But here, since the growth is a so-called Gevrey growth, the usual Borel resummation does not work. A new kind of resummation has to be done, which was developed by Icall. It's called Borel-Icall resummation. So we have to do the Borel-Icall resummation of this one. And once we do that, you get a completely closed form expression for this whole series over here. Okay, so that's the source piece over here. The whole bad thing about the perturbation theory has gone over here. And after a Borel resummation, you get a completely closed form expression. Now you see expectation of value of phi is become a completely closed form expression of this particular way. And this is a PV stand for the principal value integral. AK is the propagator. Sigma is as yet unknown. And it determines what is the Glauber-Sudarshan state. Curly A I've already defined to you. And you see it's e to the power minus s over g 1/2 times that particular thing. We now make a few observations. Of course, the whole series in the path integral is summed up completely. The final answer is a wave function renormalization of the tree level answer. So this is the tree level answer. You can see final answer becomes some kind of a wave function renormalization. Even if you take A is even or odd, one can show that it has only one pole in the Borel axis. And this particular compact form, this principal value, if you actually expand it, if you expand this, you can see that this is exactly written as an instanton saddle and the corresponding fluctuation determinant over all infinite instances. So what has happened is that the asymptotic in lambda 5-4 theory, there are complex instantons are also there. There is no real instanton, there are actually complex instanton. And they actually contribute to the saddle in this particular way. And then there is a fluctuation determinant. So this take this particular form, which takes the expected form of n, as I said. So that's the reason of putting everything in this particular form. Now, however, an even more surprising result appears if you identify, if you make this identification expectation value of phi to be equal to this. Now we actually computed expectation value of phi. So this is equal to that guy over here. And now you see something very interesting. This whole thing is like lambda 4/3, lambda 2 minus 4/3. And this whole thing is like t to the power of minus 8/3. So that means since A is the propagator we know, we can actually figure out what kind of Glauber-Sudarshan state we want, whose Fourier integral give rise to t to the power of minus 8/3. And then this whole factor over here will give rise to the cosmological constant. Of course, there is a much more compelling reason to make this split like that, which I'll not have time to discuss, but there is a much stronger compelling reason to say that this is exactly that and this is exactly that. So we now have been able to quantify what sigma we want to get this particular kind of background. In the process, we have a closed form expression for lambda. And the closed form expression for lambda tells us that is given by that particular thing over here, where AS, so you do a principal value integral over here. So you may immediately ask whether this is positive or not. If it is negative, then all our work will fail. It turns out that no matter what sign A takes, it's always a positive definite quantity. If A is negative, of course, it's positive. If A is positive, then one has to do a principal value calculation. And there is one pole in the Borel axis, and one can show that this integral is always positive definite. So this thing which we call as a cosmological constant is indeed a positive definite quantity. Can this be made small? Now it appears that it can be made small, but we are not sure yet. This is a work in progress. Now you can ask how small? Can this be made 10 to the power of minus 120 times m Planck square? Well, we have absolutely no idea whether we can do that or not. But don't be alarmed, we haven't solved the cosmological constant problem. This is just a scalar field model. The actual analysis will be very hard to deal with. However, our analysis suggests that maybe dark energy is a cumulative effect coming from summation of all quantum terms and is completely invisible at order by order computation. So that is the reason from the very beginning I was saying that we never cut off. If you remove some quantum term and all, you'll never see cosmology constant coming up because everything is an emergent quantity over here. It could be that maybe the dark energy is a cumulative effect coming from all the summation of all quantum terms. So it's also an emergent effect. So it's unlikely that any vacuum configuration could reproduce it. And as they say, the whole is greater than the sum of its parts. So you see, after you sum up everything, suddenly a new thing appears. First, the space-time appears as an emergent quantity, and the cosmological constant appears after you sum up the whole Borel resummation, then you see something positive coming up. Now, of course, it's not clear whether it can be small or big, but now our analysis might also provide hints on precise reconciliation of GR with quantum mechanics. For example, all non-trivial general relativity configuration are like Glauber-Sudarshan states in quantum world. And the GR equation of motion should be like the Schwinger-Dyson equation. This could probably make Einstein happy. So I think I took a little bit longer than usual. So here is the summary of my talk. I'll just show a table to summarize. So here is a vacuum configuration. It's replaced by what? So if I take type 2, type 1 heterotic, I have to replace by M theory and duality sequence. The de Sitter spacetime, which we expect in vacuum, is replaced by an excited state of this form. Fluctuation over de Sitter, I didn't have time to discuss. It's a new kind of state over here. The Transplanckian bound appears to be, in our language, is when the type 2A coupling is smaller than 1. Black hole in de Sitter appears to be another excited state. The equation of motion appears to be Schwinger-Dyson equation now. On-shell states in vacuum, there are no on-shell state. We only have off-shell states. Off-shell state, on the other hand, are non-local quantum term. Feynman diagram are replaced by nodal diagrams. The space-time metric is an emergent quantity in our language. The conformal time is, instead of -infinity to 0, we only have a time over here. The internal metric is an emergent quantity over here. The cosmological constant, as I told you, appears after Borel resummation. Existence of effective field theory turns out to be something interesting, that derivative has to be positive power, but I didn't have time to talk. The quantum tunneling in here appears to be real and complex instanton. The non-perturbative effect, which we see in vacuum, are actually Borel resummation of Gevrey series. Open QFT replaced by Wilsonian one. 0-point energy, there is no 0-point energy contribution. The vacuum with SUSY is broken spontaneously in our analysis. And so on. Moduli stabilization is replaced by that. No Boltzmann brane, of course. The background fluxes is an emergent quantity. The 7 branes is a new state in the theory, another top-knot state. Gauge field on the 7 brane become localized fluxes, orientifold 7 plane become that. So thank you for your attention.
Thank you very much, Keshav, for this very nice talk. Do we have questions from the audience? Please feel free to unmute yourselves and ask.
I have a question.
Yeah.
Like, see, the main problem with the cosmological constant is the fact that it is so small.
That's right.
Yeah. So, I mean, do you envisage any way of showing that in your model?
Actually, we are working on something. Right now, I don't know whether it can be made very small. We do see that it can be made small. I don't know how small it will become, or plus it's a scalar field model, of course, we are taking. But right now, I don't know how small it can be. It is definitely positive quantity, but it's not clear how small it can be.
Also, another question is whether taking the Wheeler-DeWitt equation point of view can have any consequences, because, I mean...
Yeah. Yeah, I know what you are asking over here. Joydeep and I discussed quite a bit on this aspects of that thing. It's a little bit different. We are not taking, since we are not dealing with vacuum configuration and all, the Wheeler-DeWitt equation of this R equal to 0, that is not, does not appear in our analysis.
No, Wheeler-DeWitt doesn't necessarily, I mean, it includes all sorts of excited states as well, right? I mean,
yes, you are saying that maybe this GS state could also appear as a solution of that one, huh?
Yeah.
Could be. It could be, yeah.
Any other questions?
Keshav, I just have one more quick question. So, if I'm not mistaken, I think it is when you talk about the M theory uplift, of your type 2B ansatz that you were initially considering, and possibly also implying later, even in the emergent metric picture, was, I think, would probably be summarized as a 362 uplift. In the sense
As a
that
what? So,
as a 362 uplift, in the sense that you have locally R12 times the sixfold, which is non-scalar, times the torus.
Yeah.
Now is there, I mean, why is it not, for example, a 461? Why don't you have an R13 times a non-scalar times an M30 circle?
Yes. It turns out that, of course, that would be much easier. 461 would have been 4 plus 7 would have been much easier thing to do. It turns out that the equation of motion, or the study of these, the way we did using the scaling analysis and all, it's much harder to do using 4 plus 7 or 461 instead of 362.
I see. And is there something more that can be said about the geometry of M6? You said it could be non-complex. Is there something more that can be said, or?
Yes, we can actually quantify this, the topology a little bit more. I can tell you in private how exactly.
Okay. All right. Thanks.
Do we have more questions for Keshav? Okay, if not, let's thank Keshav again. Thank you, Keshav. That was very nice.
Thank you. Thank you. Thanks.
Thank you.
Thank you. Bye.
Bye, everyone. See you next week.
Bye.
Bye.